Ya estás transmitiendo en vivo.
Ya te está transmitiendo en vivo. ¿Me confirma Juan que la puede ver?
Ah, claro. Porque tienen que hacer el inicio acá en YouTube.
Ya.
No, el inicio. Dice que...
A las 9:05.
Yo no sé. Se supone que debería verse, ¿no?
Me salgo de... No se sale. Ah, ya.
No es Rockland Center for Astrophysics.
Buenos días.
Buen día,
¿Ah, sí?
No.
¿Cómo hizo aquel usted? ¿Antes de acá? Sí.
Sí,
Profe. Ahora ya valoro más la profesión de los youtubers. Los problemas de transmisión en YouTube, ya valoro más la profesión de los youtubers. Claro, mismo.
Buenos días, hola. ¿Cómo estás? ¿Cómo te va?
¿La profe?
Hola, yo pensé que era virtual.
No,
Que Javier estaba en
todavía no.
Noruega. ¿Qué pasa? ¿Cómo va todo?
El sábado ya había América.
Ah, el sábado día máximo.
América.
Ah, sí. Pues, ¿cuál es? Esa. Sí.
Juan, ¿ve algo allá?
Que es el de NV. A ver, sí.
Es una DM, una empresa que trabaja.
Ah, la de Juan Camilo.
Sí, pero yo no sé las significados de esas siglas.
Cierto, cierto. Pero yo pensé que era el
¿Listo? Ahí se ve, ¿no, Juan? ¿Me confirma? Ahí se ve, ¿no, Juan? Ya que sí. Yo creería, profe, que...
¿Y está el enlace de YouTube también?
Sí, yo creía que con la bendición de que sea de Dios, de lo que sea que exista. Yo creo que estamos listos.
Bueno, entonces comencemos. Bueno, muy buenos días a todos. Vamos a comenzar entonces con esa sustentación de tesis de la maestría en Ciencias Astronomía. Va hoy a exponer entonces su tesis el estudiante Francisco Javier Ordoñez Araujo. La tesis se llama Dynamics of the Cold SolarChromosphere Observed with ALMA. El director es el profesor Benjamín Calvo Mozo del Observatorio Astronómico Nacional y el codirector es el profesor Juan Camilo Guevara Gómez del Roseland Center for Solar Physics. Tenemos hoy como jurados al profesor Shaheen Jafarzadeh del Max Planck Institute for Solar System Research y al profesor Giovanni Pinzón Estrada del Observatorio Astronómico Nacional. Bien, el orden de esa presentación es el siguiente. Primero, el estudiante tendrá 45 minutos para hacer la exposición. Luego de eso, daremos paso a las preguntas por parte de los jurados. Y finalmente, tendremos comentarios por parte del director y codirector. Bien, entonces, Francisco Javier, ¿puede comenzar?
Hi everyone, thank you for coming here. Today I'm going to do the presentation of my master thesis titled Dynamics of the Cold Solar Chromosphere Observing ALMA. I carry on this project with the assist of Professor Benjamin, Juan Camilo Guevara Gomez, and with the collaboration of Sven with the Maya. I would like to start this presentation showing you the general structures. My presentation is broken down into 6 parts. And the first part, I will present you a general description of the solar atmosphere, and also we will go through some models that try to describe these layers. In the second part, I will present the proposal and a specific and general objective of my thesis. In the third part, I will present the instruments and data that I used in my project. And also I will show you a short video where you can share the cold events that I studied. Finally, in the last three parts, I will present the method and results that we found in my thesis. And at the end of the presentation, I will present a summary and conclusion of my thesis. Starting with the general descriptions of solar atmosphere, over here, this is how looks the solar atmosphere, observed with different filters, starting with the deepest layer, the photosphere. This layer is characterized by the strong presence of convective cells and solid spots in regions where the magnetic field is strong. Above the photosphere, we find the chromosphere. This is the layer that I studied in my thesis. And above this layer, we find the transition region and the corona. Now, before to start show you some models to try to describe these layers, let me tell you that in my thesis, I studied quite some regions, and it's because of this, I would like to start this presentation showing you one of the earliest models to try to describe these layers in acquired zone regions. This model is called BAL model. This model was developed by Bernasa and collaborators, and in their model, Bernasa and collaborators made a fit in height and in temperature in order to reproduce observations in many lights, such as Lyman alpha. And through this process, they found this profile temperature that describe how it's changing the temperature as function in the height in the solar atmosphere. We can observe here the lowest temperature that predicts this model is around 4,500 kelvins. These models in general represented a great advance in our understanding in solar atmosphere, but unfortunately this model presents some limitations, such as the static models that didn't take into account dynamic effects, and also they have problem with sea observations. Let me make emphasis in sea observations. These problems appear when noise and air reported strong emissions in CO molecules, and when they use those observations to predict the lowest temperature of the solar atmosphere, they found that actually the lowest temperature of this layer is around 3,500 kelvins. And now we can observe that we have two different values for temperature corresponding with the same region of the solar atmosphere. That is a little weird. In these times was a big discussion that actually exacerbated when Solanki in 1994 reported a strong emission of the CO molecules at atmospheric height. And now the question is, okay, why Solanki, airs, and noise report a chromosphere with low temperature when BAL model reports a chromosphere that is mainly hot? And in this point, we have this question: is the chromosphere hot or cold? What is happening here? And in order to find a model that explains these observations, Ayres proposed his models, and in these models, Ayres combines observation of BAL and CO, and it's because of this in the literature we find that the BAL Ayres models is referred as the model with two components: a hot component related with BAL observation and a cold component described by CO observations. Through these models, Ayres successfully reproduce CO observations and also reproduce Solanki observations. And here, for example, we have this picture describing how looks the solar chromosphere under the vision of BAL model, where we can observe a highly homogeneous atmosphere. And we can observe here that the minimum temperature is limited in a thin layer of the solar atmosphere. But on the other hand, with these Ayres models, he proposed these visions with a highly dynamic atmosphere, where we can observe an expansion of the minimum temperature at atmospheric height in order to explain Solanki observations. In this point, these models represented a great advance in our understanding. But unfortunately, these models also present limitations, such as didn't take into account dynamic effects, and also just predict small clouds of CO. Now, we require a model that incorporates three important elements. The first, CO observations. the second important element is bulk observations, and we require a model to take into account dynamic effects. One of the earliest models that incorporate these three elements was proposed by Carson and Stein in 1995. In their model, they predict that the solar chromosphere is constantly forced by P modes in the solar photosphere, and these oscillations produce waves that propagate outward in the solar atmosphere. And when these things happens, two important things appear. The first, do the density decrease with the height, the speed with this wave propagate outwards increase, and when reach chromospheric height, turn into shock wave. And the second important thing is this shock wave changes dramatically the temperature in the solar atmosphere, because in the front of the wave we have a compression of the gas and increase the density. But in this point we can explain why bulk observe a chromosphere mainly hot, but in post-shock regions we have an expansion of the gas, and under these approximations, Carson and Stein open the possibility that CO formations can form in these regions where we have a low temperature. Also, this limitation, unfortunately presents limitations because it's a one-dimensional simulations, and in order to have a more realistic description of the solar atmosphere, we require a three-dimensional simulations of these layers. Currently in solar physics, we have mainly two codes, bifrost and cobalt. Here we are observing a vertical slide of cobalt simulations taken from with the Maya paper. Here we can observe regions with high temperature that was reported by Carson and Stein, and also we observe regions with a low temperature. Leonard, using Bifrost, observed that the propagation of this shock wave could reach a height around 2,000 kilometers above photosphere. And under these observations, Leonard opened the possibility to explain Solanke observations and also agree with Carson and Stein simulations. But unfortunately, with Maya observes the opposite results, because in posterior regions, when Maya studied the physical condition in those localities, he found that the long chemical rate reaction and the frequent pass of this shock wave at atmospheric height prevent the formation of a mass quantity of CO. In this point, we are in presence of an open debate, because today we don't understand what is the real nature of these CO observations. And in this context, we find that Jonathan Stalford said that we require better instruments per telescope with a high spatial and spectral resolution in order to understand what is the real nature of these CO observations. After to show you this general description of the solar atmosphere, show you some models and this open debate, in my thesis, we studied these cold regions observed with ALMA in band 3 in a quiet zone region. Now, I will show you the general and specific objectives. Our idea was to study what is the dynamic properties and evolution of these cold events observed with ALMA in band 3. To do this, my first specific objective, the idea was to make a characterizations of these events, such as lifetime, typical size, and velocity of these events. And then my second specific object, the idea was compare the dynamic evolution of these events and how looks these cold features in SDO and IRIS observations. As you can observe here in my specific objects, we didn't tackle the CO problems. The idea with this project was design a diagnostic tool that in the future could be used to decide which model is right or wrong in order to explain the CO observations. And also, the idea with this project, the results that we found could be used as insight to enhance the correlative simulations that we have for the solar atmosphere. After to clarify this point, this general specific and general objective for my thesis, let me show you the instruments that I use. Here, we can observe radio interferometer, ALMA radio interferometer, SDO, and IRIS. I studied the D06 regions taken from SALSA database. In particular, we observe here the filters that I used, starting with AIA 1600 and 304, IRIS 2786, and ALMA band 3. In the next slide, I will present you how looks these cold events that I studied. At the bottom left part of the video, you find the spatial resolution of ALMA 3. At the bottom right, you find the spatial scale of the video, and at the top right, you find the scale, the temperature scale of these maps. And here in this video, you can observe that there are mainly two types of features. The first is region with high bright temperature, and also you observe these cold events that I studied in my thesis, and you can observe that they have an apparent motion, sometimes appear, disappear, and the idea in my thesis was to study what is made a characterization of the properties of this cold feature, but also figure out what is happening here, which physical phenomena could produce these events. After to clarify this point, let me show you the spatial location of the regions that we studied. And we can observe here the regions I studied is located in the southern part of the soil. And in this magnetogram, as I said before, you can observe that the region that I studied is basically regions with low magnetic fields. It's quite some regions. Now, after to show you this cold events and how looks this cold feature that I studied, I would like to start with my first specific objects that rely on the dynamic property, the study of the dynamic property of these cold events. And the first part, we developed a method to align images from IRIS, ALMA, and SDO. I will explain details, with more details in the next slide, this part. The second part of the method, we made an identification of these cold events, and to do this, we use physical criteria, such as a spatial resolution of the instruments. Also, we define a threshold that allows us to consider when a pixel is hot or cold. And also, we select a portion of the ALMA field of view to search for cold events. And after the identification of these events, we made a tracking and elaboration of masks of these cold structures in order to identify what is the spatial expansion covering for these events. After to make these parts, the tracking of the elaboration of the masks, we studied the dynamic properties of these cold structures. Now, let me start with the description of the method that we developed to make the alignment of the images. Here, we have, but before, let me explain you why we require to make the alignment of the images. Suppose that you have a region that is being observed with two different telescopes. As you can observe, every telescope has different field of view, cadence, and spatial resolution. And the idea is identify regions that was observed with one telescope, in our case, ALMA, in this example. How looks these regions in IRIS observations, in SDO observations? To do this, we carried out a comparison between of similarity between images using Pearson coefficient and similarity index in order to identify for which specific pixel we find the highest correlation between images. After to apply this process, we can observe here the ALMA field of view and this thermal structure observed with ALMA. When we compare with IRIS observation, we observe a clear correlation between brightness structure observed with ALMA and how correspond with the thermal structure observed with ALMA band 3. I apply the same process for SDO, and we can observe here there is a clear correlation between images, and this shows the effectiveness of the method. Now, after to start to talk about the dynamic properties, let me tell you that the idea in my work was compare the dynamic evolutions of these cold events frame to frame with ALMA and with IRIS and SDO observations. But the problem here is this instrument has different cadence. And to solve these problems, we made an interpolation of IRIS 2796, AIA 1600, and 304. And through this process, we compare frame to frame, how looks this cold events and what is the dynamic evolution of these cold features in IRIS, ALMA, SDO observations. Now, I will start to show you the total events that we detected. As you can observe here, this corresponds the average ALMA database. This bullet point is representing the total 44 events that we detected in my study. As you can observe, there is a clear correlation, again, between this thermal structure and the brightness structure observed with AIA, IRIS. At this point, we can observe that the presence of this cold events located in regions with low bright temperature. Here, we observe that the spatial location of these cold events correspond with regions with low bright in IRIS and AIA observations. Now, let me make a special emphasis in HMI observations because as you can observe here, as you can observe in these pictures, our cold events was located in regions with low values of the magnetic fields. I'm aware of the limitations that we have when we try to use HMI observation in some regions, but even though taking into account those limitations, we can identify clear structures in HMI in A subplot. We can observe or cold events is located in regions with a weak magnetic field that in the literature, where the Maya refer these regions as internet regions. Now, in order to find more information about what is the topology of the magnetic fields, we compared our results with the literature, and we found that Shaheen, one of the opponents, he studied these 06 regions, and he made an extrapolation of the magnetic field. And when we compare the spatial location of my cold events, we found that our cold events mainly located in regions with a weak magnetic field in the perpendicular component. Also, we observed a strong presence of magnetic canopies. When we compare these extrapolations, the magnetic field with the thermal structure of ALMA, we observe a clear correlation between images. When regions with a perpendicular magnetic field is observed with ALMA as regions with high bright temperature. On the other hand, regions with low bright temperature correspond with regions with the magnetic fields in the line of sight is weak, just presence of these canopies. Now, in order to identify what is the area covered by these cold events, we studied this. We tackled these questions using the masks, and you can observe here. We are showing you in this green contours the average of all masks that we found, and we can area covered by my cold events. Just extend covering internetwork regions. This when we study how is the temperature distributions inside these cold events, we found these distributions with reaching a peak in this distribution around 6,700 kelvins, and the functional weight of these distributions agree with the Maya paper published in 2020, when he said that regions with these distributions could be associated with internet regions or less. And here we have in presence of our results that suggest us that the spatial location of cold events mainly limited to appear in regions with low magnetic fields, referring the literature with the Maya as internetwork regions. And that's actually I agree with Henry paper when he said in his paper of 2021 that the probability to detect dynamic effects, dynamic features associated with shockwave increase in internetwork regions where the magnetic field is weak. After to show you this characterization of the spatial location of these cold events, let's move on with the dynamic properties of these cold events. Here, we can observe the typical, this corresponds to the diameter of my cold structures, and we can observe that the typical size of these events is around 1.8 or 3.5 arcoseconds, reaching a peak in the distributions at 2.3 arcoseconds. These values of size for these cold events is close to the typical size of photospheric emulations, and this may suggest possible relationship between the generation of this shockwave in intergranular regions and the propagation of this shockwave at chromospheric height. Now, in the lifetimes that we found for all 44 events of these distributions, we can observe the average value of life that we observed corresponding to the lifetime is around 2.5 minutes. Related with the velocity, we found here the total component velocity that is represented in the components. We find that it's centered around 0, and the total velocity reach a bit between 8 or 9 kilometers per second. This typical value for this cold events is around 8 or 20 kilometers per second, and this agree with the Maya observations in regions affected by shockwave. And if you can observe, these dynamic properties suggest us that the cold events that we studied could be associated a shockwave, could be generated by shockwave. This could be important in my second specific object because we used this insight to interpret the results that we found in my second objective. Now we have here some important quantities for the distributions, such as average, maximum, minimum of this related with the temperature of these cold events, tangential velocity, typical size of these events, and also lifetimes. With this, we fulfill my four specific objectives, but now we have just these questions. Okay, that's it all. What about the dynamic evolution of these cold events, and how looks these cold structures in SDO and IRIS observations? In order to find the answer for these questions, we applied this method. Again, starting with the alignment of image, that was an important part of my thesis. And after we generate time distance diagrams in this location in where we detect these cold structures, we took a small window of 6 arcoseconds and we studied how looks the evolution of these cold events in time distance diagrams using ALMA band 3, quiet regions again, IRIS 2796, AIA 1600, and 304. Related with, and after the estimation of these time distance diagrams, we studied the evolution of these cold events, how looks these cold events in these time distance diagrams, and through the study of these diagrams, we estimate a formation height for the data that we used. Now, let me show you how looks the evolution of these cold events. Here, in the first column, we have time distance diagrams along x-axis, time distance diagrams along y-axis, and the average of time distance diagrams corresponding with these curves. In these points, it's important to remember, my first specific objectives, the properties that we found suggest us that those cold features that we studied could be associated with shockwave. And if you remember, Carson, Bifrost, and Cobalt simulation suggest us that the propagation of this shockwave changed dramatically the temperature of the solar atmospheres. And in the front of the way of this shockwave, we have a compression of the gas, and because of this, we have an increase in temperature. But after, as you can observe here, in the posterior region, we have an expansion of the gas. In the lifetime that we estimate for my cold events, we found that the average lifetime is around 2.5 minutes. And we can observe here this period behavior have a period more or less between 2 minutes, 3 minutes. That's agree with the results that we found in my four specific objects. And we can also observe a clear evidence of the shockwave effects, because we have here an expansion of the gas and after a compression of the gas, and here an expansion, and that means an increasing temperature, increasing temperature, decreasing temperature, increasing temperature, and this behavior was observed in all 44 regions that we studied. Now, what about the literature? The literature agree with these results? Fortunately, yes. And here we observed with the Maya results, he used cobalt simulations to obtain these synthetic bright temperature maps. And particularly, I will make emphasis in 3 millimeters because I use the data from ALMA in ALMA band 3 that is centered in 3 millimeters, 100 gigahertz. And here we can observe the effect of the propagation of shockwave and how this shockwave affect millimeter emissions of the solar atmosphere. And we can observe similar behavior, decreasing temperatures, increasing temperature, decrease, and this is an effect of the propagation of shockwave. I'm aware of the difference amplitude, but this is just an effect because with ALMA we have lower resolution compared with global simulations. But here we are in presence again of propagation of this shockwave and how this wave affect ALMA observations in 3 millimeters. And now we can ask, okay, what about the other telescope? So IRIS and SDO, those telescopes also, the observation of those telescopes also affected by the propagation of shockwave? The answer is yes. Here, I'm showing you an example of a cold event that we detected. Here we observe time distance diagrams along y-axis and its axis. Time distance diagram for HMI, AIA 6300, IRIS 2796, ALMA band 3, and AIA 304. Let me make a special emphasis in this part. Here we can observe initially regions with low bright detected by AIA 1600, and after in IRIS 2796 with a time delay, just a couple of seconds later, IRIS detected cold, the same events, but with a temporal delay, and finally, ALMA band 3 observed regions with low bright temperature. In this point, if we take into account this all evidence that suggests of the propagation of this shockwave, here we can interpret these results as strong evidence of propagation of shockwave through the solar atmosphere. Here, starting with the detection of the shockwave by AIA 1600, and after the propagation of this shockwave reached IRIS 2796 line 4, observed the same events with a time delay, and finally ALMA band 3 observed the cold events produced by this shockwave. What about HMI? We tried to incorporate these results, but unfortunately, when we made the average, the time distance diagram, we found that the average value for the magnetic field were close to the noise estimated by the instruments, and it's because of this we just discard this data. Related with AIA 304, we didn't observe the propagation of this shockwave. We speculate that maybe this light is forming above solar, in the upper chromosphere, maybe transition regions, and in those regions the density is low, and these physical conditions could prevent the propagation of this shockwave. But now, after to give you this general description of how this shockwave affect AIA and IRIS 2796 observations, we used this time delay to estimate formation height for IRIS 2796 and ALMA band 3. We made this process studying this time delay. Here we have again the evidence of the propagation of shockwave. These time distance diagrams correspond with these cold events detected when crossing this green square. And when we take the average of these time distance diagrams, we find these three light curves. And we can observe here a clear time delay between observations. And through the estimations of this time delay for whole 44 events that we detected in my study, we found an average time delay between 1600 and IRIS 2796 around 20 seconds, and between 1600 and ALMA 3 around 100 seconds. Using these time delays and under the assumption of a typical propagation of shock waves around 8 kilometers per second, these values agree with observations in simulations. Using these equations, we estimate high difference formation for these lines. And now, in order to calibrate our high difference formations, we used these values for AIA 1600 life force reported by Carson and this author in 2005. Again, under the assumption of propagation of this wave 8 kilometers per second. Using this equation and the data that I mentioned before, we estimate that ALMA 3 is forming around 1200 kilometers above the photosphere. Actually, it's above tau equal 1 for 500 nanometers, but yes, we can say just above the photosphere. Here in IRIS, for IRIS 2796, we found a high formation around 600 kilometers above the photosphere. The results that we found for ALMA agreed with the Maya and Lokisheva papers published in 2016 and 2015. In particular, for IRIS 27, my results agree with simulations carried out by Thiago Pereira and Leonard. And here, through this process, through estimation of this time distance, for estimation of these high formations, we reinforce our idea that these cold features is being produced by shock wave. Here, we have a general summary of the results of my thesis. Starting in my first specific objectives, we can conclude two important things. The first, the spatial location of the cold events that we detected limited to appear in regions with a weak magnetic fields. This agreed with Henry paper because he said that the probability to detect dynamic features generated by shock wave increased in regions with a weak, and that's exactly what we observed. And also, we observed that dynamic properties such as lifetime and size or temperature distributions suggest us that we are in presence of shockwave features, and we can associate those typical properties that we observe could correspond with shockwave features generated by these waves that generate in the photosphere and propagate outward in the solar atmosphere. And my second specific objective, we found that the dynamic evolution of these cold events that we observe in time distance diagrams and the light course of these diagrams suggest us that this wave affect dramatically the temperature that observed ALMA 3, and the time profiles agree with the Maya paper and Henry papers and their simulations when they use Bifrost cobalt. With the Maya used Bifrost in these papers, but Henry used Bifrost and Carson model. Under the assumption of the propagation wave, we observed that when we estimate the formation height under the assumption of this shock wave that propagate in these cold regions, we found that the values that we estimate for the formation height of IRIS 2796 and ALMA 3 agree with values reported in the literature, and this again reinforces our idea that these cold features could be generated by this propagation of shock wave. Finally, in my first, we didn't observe propagation of shock wave at AIA 304. Again, we speculated that maybe it's forming in the in transition regions, upper conifers, in those regions density is pretty low. In general, as you can observe in my thesis, and the conclusion, you can observe that with this study we enhance our understanding of the thermal structure of the solar atmosphere, and we also observe that these models and these dynamic properties that we found, and this dynamic evolution of these cold events in the future we can use these results as a diagnostic tool to determine which models is right or wrong in order to explain CO observations, and also we can use these results as input to enhance the cooling simulations that we have in the SolarChromosphere. Before to finish this presentation, let me tell you that I am aware of the limitation of when we try to use ALMA boundary observations, because the resolution is low, and this has a strong impact in the dynamic properties that I showed you today. And it's because of this, we think that we can enhance these results if we use artificial intelligence to make the convolutions of the images. And this idea was proposed by Henry in his recent paper of 2023, more or less. He said that we can increase the resolution of the ALMA boundary using this artificial intelligence, and through this process, we can enhance the static and descriptions of these cloud events. Finally, I would like to take these few minutes, just a couple of seconds, I guess, to say thank you so much. I want to say thank you for the Tesis for giving me the opportunity to here and for cheering me up in of my thesis. And also I want to say thank you for all professor for me, for giving me advice. I want to say thank you for Thesis, for giving me the opportunity today at research taking there. And a special thanks for Sven with Maya for supporting me in that research stay and help me to obtain the result that I showed you today. And also a special thanks for my advisor, Professor Benjamin. Thank you for Juan Camilo Guevara Gomez, and Shaheen for being the opponents, and Professor Giovanni for being the opponents of this thesis. I guess that now I start the hardest part of these presentations, questions. Which I would like to close with this a little head up, I guess. So I guess I start the questions.
Bueno, muchas gracias, Francisco Javier. Entonces vamos a pasar a las preguntas. Now I would like to introduce Professor Shaheen Jafarzadeh from the Max Planck Institute for Solar System Research. Hello, Professor Shaheen. How are you? Okay, thank you for your participation as a jury member of this master thesis. Now I give Professor Shaheen the opportunity to ask the question that you consider to Francisco Javier.
Sorry, can you repeat here? I couldn't understand. There are many noise. Sure. To answer your questions, let me show you this. I prepared some slides for this question. Let me give me a couple of seconds. But yes, I understand the question. I'm just searching for slides to answer the question of Professor Shaheen. Here, for some, here you can consider. No, sorry. Let me show you here. Is the 25 presentation. Just let me make this. Sorry, technical problems. Here. The advantage to use millimeter observations, that is, as has been reported in 2016, he said that this light force under thermodynamic equilibriums. In these conditions, we can associate the source light as a black body using these equations. And now, if you take into account the wavelengths, or the millimeter wavelength of associated with ALMA battery, 100 gigahertz, and when we estimate how is the relation between the photons emitted by these layers, photospectrospheres, in the millimeter emissions, and the thermal energy in those localities, we found that we can use Rayleigh-Jeans approximations. And under this approximation, we have a linear relationship between a specific intensity observed with ALMA and an estimation of the brightness temperatures. This is just an approximations, but according to Lokisheva and Sven, they say that this is a great approximation in order to an approximation of the real temperature of the solar atmosphere. But when we compare these results with this great condition with ultraviolet emissions, we find that those observations formed outside of the thermodynamic equilibriums, and that is a huge problem because the radiation that chromosphere emit in ultraviolet doesn't couple with the physical condition of the locality in plasma that emit that's a kind of light, and it's because of this researchers during long time expect appear ALMA, because through using ALMA we can use this great association between a specific intensity and brightness temperature, and we can map the real, we can map a great approximation of the temperature in the solar atmosphere. I guess you are trying to ask me what is the disadvantage to use ALMA observation and don't use, for example, ultraviolet observations. That is right or wrong? Mm-hmm. The problem with radio interferometers always is the low resolutions. With the Maya and Henry reported that actually these color structures were not completely resolved with ALMA because I is below the ALMA resolution. Here we have the ALMA resolution of the data that I use around 1.7 echoseconds, and the typical size of this color dimensions are around 1 ecosecond, 1.5 ecosecond. Here, even Lokisheva made a study how affect the low resolution or decrease or the degradation of the resolution, this linear relationship between brightness temperature and a specific intensity. And she said that it's a good still, even with the low spatial resolution that we have with ALMA, we can use those data to study the dynamic evolution of general study the SolarChromosphere. But yes, I agree with the limitation of the ALMA. The main limitation is the low resolution, and it's because of this. For example, Henry suggests that we can use artificial intelligence to increase this resolution. Even I prepared this slide when we can observe here a clear degradation between images, and we can observe here how it looks this this event with high spatial resolutions. I don't remember exactly the resolution, but it's some, I guess it's around 6 kilometers. 60, yeah, 60 kilometers. And when we apply the convolution with ALMA observation, we can observe here that there is no clear result of these color structures. But yes, it's because of this I said these properties that we found, we can take into account that have a strong impact with the low resolutions. Yes, it's at the moments that we can just do this with ALMA. Um, I don't know if I guess I met my. Yeah. Uh, And at this point, I validate the alignment of the images. Initially, in a visual inspection, we can observe a clear correlation between the thermal structures and the brightness structure observed with other telescopes. But also, when I read the paper of SALSA database, I found that in Rosland Center for Solar Physics, they estimate um, a coordinate reference for the center field of view of ALMA that we just present a discrepancy around 5%. I don't remember exactly the values, but it's pretty low. And this was a way that I check or inspect if my alignment method that we developed is right. Initially, first is visual inspection, and also compare with SALSA paper. Thank you. To answer your question, yes, initially we published this an example in GitHub, and after to finish this process of the defense, I will write some library to other people can use because I agree with you. This took me along at least 4 months understand what is the process, the complete details, and there are many details that I omit to mention, such as rescale of the images, rotate, and interpolate intensities. But it's because of this I think that it's a great idea, made a documentation so other people use. I like the results, and also when I compared with papers, and actually I found a better results in my method. And that was very nice. Thank you for the opinions. Ah, yeah, I got your point. Yeah, um, maybe is I should say that the magnetic field is weak, just a very high because we don't have information how what is the value of the magnetic field of these magnetic loops. But yes, I agree with you. In general, the magnetic field in the photosphere is weak. But in particular, in this internetwork regions, the average magnetic field is around 20 minus 20 gauss. Yes, but yes, you are right. I should say that actually is also high. Ah, yeah, yeah, yeah. When I found initially we tried to use observation magnetic fields with a close presence of these loops, like this zero one observation, and we found that the spatial or the geometry of these cold events was completely different. In, for example, in presence of these strong loops, we found fibril structures, and it's because of this we say, okay, in quiet zones, many researchers reported that just shockwave, and the evidence that we found suggests us that we are in presence of shockwave features. But what about these cold events? When I compared in the literature, I found these possible other physical processes that could generate these cold events. These authors say that if we are in presence of these loops, they can transport electrons with general material reaching in electrons density, and this could produce cold events observed with ALMA band 3. But in this case, we can observe like a fibril structures. And in my thesis, I didn't observe those structures. I just observed spherical, even circles, ellipses, and similar to this that are related with the um, geometric of this called events, similar to the events detected by Henry in bright point regions, in bright point features generated by shockwave. And it's because of this I say, okay, maybe it's right. We made this use or suggest the proper this feature, this called features could generate by shockwave. And it's because of this we try to validate that hypothesis, estimating the formation height for the instruments, and we found those values. And I say, okay, this reinforces our idea, but we should say that this is just a suggestion. This result just suggests we are not completely sure because always there are other phenomena that could appear, and even if we take into account the low resolution of the instruments that we have with ALMA, appear other phenomena that we didn't observe, as you said.
Okay, thank you very much. Ahora le damos la... Ok, thank you. Ahora entonces le damos la palabra al profesor Giovanni Pinzón, que es profesor de Observatorio Astronómico Nacional, y pues puede hacer las preguntas.
Okay. Javier, congratulations for such a nice work, and the manuscript is very well written, and the presentation was amazing, very nice work, as I said, beyond the expectations from our master program in astronomy. Then congratulations. I have just a few questions, most of them related with the question of the other referee. And well, the first one is concerning the wavelengths you consider for your study. I mean, the spectral window defined by ALMA. Could you please remind us why did you choose this CO molecule, and if you could remind us the main features in the ALMA window, why vibrational transitions and not even translations, I mean, processing the radiation of the molecule.
So I expected that question, and to answer that question, I before to start the presentation, I said that we didn't tackle the CEO problems because even the observations that noise and errors observed in 4.7 and in 4.7 microwave emit outside the bands we observe with ALMA. ALMA center in 1 millimeter is just 2.5 millimeter and 3.5 millimeter more or less. As to clarify this, I searched in the literature. Okay, what about CO observations? ALMA could observe these radiations, and we found that Maya in 2016, he said that under these conditions we can observe this transition of these molecules. In particular, in these bands, is outside the band 3 observation. I don't know what bands is. But in this paper, also as Ben highlights that it's so difficult to estimate which lines could be rotational rotational emissions we can observe with or emitted by the SolarChromosphere, because the constantly change of the physical conditions in the SolarChromosphere do the propagation of shockwave not only in vertical directions, also propagate in tangential velocity and tangential directions, and made that this observation or estimations of the CO emissions, or a particular line emission for CO molecules that come very high, was pretty difficult to estimate. And to answer your question is, I expect in general in this COSA observations, quite something number 1-3, we could have contribution but at the moment I found that there is no way to estimate which specific lines that emit CO molecules could appear in ALMA band 3. Actually, it's because of this Stauffer say that will require spectrograms with high spatial and spectral resolutions, because again in ALMA we just observing a band and this empty radiation for many processes. And because of this, it's pretty hard make that distinctions of the CO observations. Even as Ben predicts this change in brightness temperature produced by CO observations, but actually when we observe the noise estimate in the brightness temperature for ALMA band 3, we found that actually it's almost 100 Kelvin. I mean, it's below, even it's inside, it's below the noise estimate by ALMA band 3, and it's because of this I say, okay, at the moment it's just an open debate, and the idea with this is just decide a diagnostic tool
Okay, Javier, the another question is how you consider the existence of shock waves using your measurements of temperature in the high chromosphere using CO molecules. You could go a little bit in deep in this reason.
I understand that you are trying to ask me if I did in the process that could generate shock wave. That's it, right?
No, you measure temperature, cyclic or periodic behavioral temperature. Why do you conclude, or what are the main reasons for concluding that this temperature behavior leads to shock wave formation?
First, if you remember, Leonard observed that the propagation of this shock wave could reach around 2,000 kilometers of the photosphere. Similar result was observed by Carson and Stein. And here, we estimate that actually ALMA boundary, even in the results here, we can observe in the literature that the line formation from ALMA boundary is around 1,200 kilometers above the photosphere. And it's because of this, we can interpret this behavior that we observe of these oscillations of the propagation of this shock wave, because we have this similar behavior, propagation of shock wave every between 2 or 3 minutes, and this produces an increase in temperature, decrease in temperature. If you remember my presentations, these time profiles, these profiles in temperatures that we found agree with regions studied by with the Maya, in particular in the regions affected by shock wave. And it's because of this for us made sense, made us suggest that these cold events could be produced by this propagation of shock wave. But as Shaheen said, there are other phenomena that can produce these cold structures, and it's because of the we just suggest that could produced by shock wave.
Can you predict the direction of such shock waves from your data?
I compared in this part here in the literature. I found that actually there are mainly 2 processes that could produce this shock wave. One of them is P modes, photosphere oscillation. This push plasma and force in the chromosphere, and this generate wave that propagate outward, and to the density decrease, you can observe this wave reach a velocity above the typical velocity of the suns in those locality. But in those studies, I didn't found typical size, and just found a little information in a paper that was published in 2001. I don't remember the author, but he said that the great collapse of the photospheric annulations perturbate the solar atmosphere, and this produces waves that propagate outward and is in the solar atmosphere. And he suggests that the typical size reached by this wave that propagate outward have more or less the same magnitude order that the granulation size. That means 1.3 arcoseconds, 100 kilometers more or less. Yes, that is the answer.
Okay, but you're assuming that the waves are coming from the bottom in vertical direction,
no.
Even if that were produced through P modes. That, I mean, are you sure that P or G modes are the main responsibles of the?
Yeah, it's P modes in this case, because I read in the literature that this P mode is reflecting the 5 minutes oscillation of the photospheres, and even in Carson model they reproduce these P modes through external pistons that force in the chromosphere, and this was a disadvantage of these models, and just produce these P modes. But not only in vertical direction, even as Ben in this article also he reported the propagation of shock wave in tangential directions, and he said that it's quite common to propagate in tangential directions. This is just a particular sample when he said no, propagated vertical is correct. But actually, in the paper you observe propagation in other directions.
Okay, and which is the role that cold regions such as CO regions are playing into the shockwave propagation? Could you speculate just from your data after you work with all this bulk of data, what are the posterior behavior of the shockwaves after meeting these cold stars at the high chromosphere?
The roles of the CO observations and how this relate with this shockwave. In one paper that studied with published with the Maya in 2006, he considered two situations. The first, the propagation of shockwave, the amount quantity of CO in the solar atmosphere, and the other situation was, okay, if we just skip the propagation of shockwave, how skip these dynamic effects affect the formation of the CO molecules. And he found that if in the chromosphere we consider that there are no shockwave, we observe a chromosphere that is mainly hot. And under this condition, he observed an amount quantity of CO, but that is not the reality. And it's because of this I say that with the Maya, when incorporate dynamic effects, he observed that in the expansion in this region, in the posterior region, we have an expansion of plasma and decreasing temperature. But unfortunately, he said that the long chemical reaction rates, I interpreted this almost the times necessary to produce these CO molecules is higher compared with the frequency pass of this shockwave. The average time of the propagation of these shockwaves are around, a shockwave is passing through the solar atmosphere around 2 or 3 minutes, more or less. And that is the role of CO molecules and how this relate with shockwave. I don't know if I answered your question.
Thank you. My last question is some kind of general question. After all this work with ALMA data and analysis, careful analysis, my question is concerning the coronal heating and the chromospheric heating solar in the sun. That is an open issue in astrophysics. After all of this work, which are the main sources from your point of view for coronal and chromospheric heating in the solar chromosphere, and which is the main role of CO regions in this scenario?
Let me search. Are you trying to ask me what is the roles of CO molecules in the context of coronal heating? Yes?
Yeah.
I can say that the problem with CO molecules is the dissociation of these molecules depends on many factors, pressures, but I read in the literature that the conditions in the upper chromosphere transition region, corona, prevents information of these CO molecules. And I don't see a contribution of CO observation in the coronal heating. Actually, in observations, researchers report the opposite, that basically CO observations take thermal energy and emit that energy through photons, and actually is cooling the chromosphere. And it's because of this I say, okay, the role is maybe is cooling the chromosphere, but actually answer the question of how this cooling could have an impact in the coronal heating. I don't know what to say. It's just
Right. I mean the chromospheric heating, which is the main
chromospheric heating,
where the energy involved into the chromospheric heating is coming from. Energy from the stem cell, or
under these visions that we observe here in quiet zone, we have mainly contributions of shockwave. It's because of the when we read in the literature, many researchers made studies on how this shock wave hit the solar chromosphere, studying bright points. You remember my video, you observe bright points. But in order to explain why the chromosphere is hot, and you can observe here, you observe mainly chromosphere hot, they just made emphasizing bright points, and it's because of this in my thesis you say, okay, but what about cold heavens? What is happening in there? I just can say that, at least for me, just an opinion, in the data that I observed, that the mainly contributions in quiet zones is just produced by propagation of this shock wave. That there are different processes that could generate this wave. Actually, as Ben reported, that he observed both contributions related with modes and collapse of brains. And that is the mainly contribution of the atmospheric head, at least for me. In quiet way.
Thank you, Javier.
Bueno, muchas gracias, profesor Giovanni. Entonces, terminadas las preguntas por parte de los evaluadores, doy la palabra al profesor Benjamín Calvo, director de la tesis, para sus comentarios.
Muchas gracias. Just a comment. This is the first thesis work here in our group using solar data from ALMA. And I think, it was due to the kind collaboration of Dr. Juan Camilo Guevara Gomez. And you carried it out successfully, so congratulations for it. And I would like to express also my thanks to Professor Sven Bademaya and the Rosvan Institute for Solar Physics for advising you, supporting you, and your stay there. And also, thank you very much, Professor Shaheen Jafarzadeh, for your comments, the report you have made for this thesis, and your questions which contributed to the next step. Maybe, surely, Francisco Javier will write a short paper on it. And also my thanks to you, your comments.
Thank you.
And well, congratulations, Javier.
Thank you, Professor.
Bueno, muchas gracias, profesor. Ahora, para finalizar, doy la palabra al profesor Juan Camilo Guevara, codirector de la tesis. Bueno, muchas gracias, profesor Javier. Claro que sí. Entonces, bueno, con eso damos por terminada la parte, digamos, de presentación, en la cual estarán pues, presentes ustedes, porque ahora tengo que pedirles que por favor se retiren para yo poder hablar con los jurados. A quienes nos acompañan por el canal de YouTube, vamos a desconectar en ese momento la transmisión y en un momento daremos a conocer el resultado de la evaluación a través del chat.
Acá puede ser. ¿Finalizó todo? Sí, si quiere finalice por allí. Finalizar.